We're going to work on my second favorite stat of all time, the analysis of variance. The analysis of variance is a means test, similar to the t-test. However, it gives you more options and more opportunities for analysis. So your independent variable, just like the t-test, is broken into categorical level data. But instead of being limited to just two levels of the independent variable, you can have two or more levels. So in my drawing, we can put up to, this one has three buckets. We can put stuff in this bucket or this bucket or this bucket. You could have more buckets if you wanted, depending on what questions you're asking. Of course, the dependent variable in that case is parametric, spread out over the curve. It's interval or ratio level data, and it presents in a way to show the effects on the independent variable. If you have two buckets or a categorical level data with two levels, then you can do a t-test. Or if you have categorical data, two levels, you can also do an ANOVA. The ANOVA, though, gives you the additional option of if you have two plus 3, 4, 5, 7, 2,962, you can do that same test. You're not limited by levels of independent variable as you are for the t-test. So let's look at some sample research questions, break it down a little bit, and analyze what it means. So in my first research question, I'm asking, is there a difference between student race on the SAT performance at the school? So SAT performance is the dependent variable. If we think about SAT performance, it's over a curve. It's not categorical, it's interval level data. And then we have race. And I'll just describe race without ethnicity. We'll just use race for the example. So we could be American Indian, we could be Asian, Black, White, Pacific Islander, or mixed. And then in this case, I have 1, 2, 3, 4, 5, 6 levels of the independent variable race. We can ask the question, does SAT performance depend on race, or does race depend on SAT performance? And obviously we want to go this way, right? SAT performance, the question is, does it depend on race? And we're going to test that. It can't be the other way around. Like we can't say that race is dependent on performance. Like your race doesn't change based on your SAT score. It is what it is. It's an independent categorical level data. Okay, so we got self-efficacy. Does student self-efficacy increase through middle school grades? So we got middle school grades, and the buckets are 6, 7, and 8. And then we've got self-efficacy, which is going to be our interval level data. Our middle school grades are categories, buckets. There are 3 levels here. Do tiered interventions, 1, 2, and 3, assist struggling students with behavioral coping strategies. So dependent behavioral strategies. And then the independent variable are tiered intervention. One, two, three. Now, it's really important. Let's make sure we understand this. The independent variable in this example is not 7th grade. It is not 8th grade. That is a level of it. The variable is middle school grades, and the level of the variable is this, 6, 7, or 8. Just like tier 2 interventions is not a variable. There's nothing changing there. Variable means change. So you can't have one thing and it be the variable. It's got to be this that can have different levels or changes available. And then finally, my last example, do SBA reading performance. We got SBA reading scores. Do they differ in schools that use different curriculum? So the type of curriculum is the independent variable, and the levels are homegrown, reading and writers workshop, or expeditionary learning, EL. Expeditionary learning is not the independent variable. It is a level of the independent variable. So once again, the t-test is used to determine whether the means of two samples are different, and the analysis of variance is used to determine whether the sample of two or more samples are different. So let's think back to my curves that we've used earlier. Let's take a look at these and talk about the difference. Okay, so in the t-test, we had two curves that we had assumed showed homogeneity of variance. The curves pretty much had the same shape to them. And the question we were asking was, do the means here and here, are they statistically similar or statistically different? And we were probably arguing at one point that these are probably different from each other. But once the curves start overlapping, we get more statistical similarity. So this would be statistically similar, statistically different, similar, different. Now in the ANOVA, we have the potential third option, right? So we could add a third curve to this dash, third curve, fourth curve, fifth curve, whatever. And the question still becomes the same. Are the means here, here, and here statistically similar or statistically different from one another? And so if they were like this, there's probably a lot of statistical similarity here. And if they were like this, then there's more likely that there's a difference there. But now, here's something kind of interesting, because in this setup, we could have something that looks like this, where these two are similar to each other, but are different from this one. So yellow and red are statistically similar, but blue is not. So when we do the test, we're going to have to do some analysis because the test is what we call an omnibus test. It just gives you the overall response. There is a difference, there is not a difference. It doesn't tell you where the difference is. You have to do some more work to figure that out. So this could be so we could have, so theoretically we'd have, this could be the case. 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 It's all dependent. And this is just three levels. If we have four, five, or six, then we have even more combinations to consider. But it's all basically the same thing. Are the means similar or different from one another? And remember, we're just comparing the means. The analysis of variance, abbreviated, it's sometimes called the ANOVA. It's used for hypothesis testing. And again, we're comparing means. Just we're doing two or more means. And it's based on the idea that the variation, which is the sum of the squares of the deviations of the values from the means of those values. As long as values are not identical, there will be variation. So SS, you will see a notation for that, sum of squares. You'll see it in the SPSS tables as well. It'll say sum of squares. So where does the source come from? The variation exists when data sets are not identical, which is like real life. Things are not the same. And it could come from different sources. And there's always leftover variation that can't be explained, and that's called the error. Again, we're going to have degrees of freedom, and those are the number of values that can free to vary once parameters are established. And so if we think of a grid of levels, then it helps explain the number of parameters. And we abbreviate that as DFF. You're going to see that on the table too. Sample variance is the average squared deviations by the mean, and it's found by dividing the variation by the degrees of freedom. So variance is variation divided by degrees of freedom. And that's also known as the mean of the squares. So it's notated as MS. And I just want to explain the components of the table. You're not going to need to calculate by hand these tables, but we're going to look at how they actually relate to one another, just so we have a sense of what's happening when the computer does the work for us. So the variance of the scores for three groups is combined into a composite group. It's called the total. You'll see that at the bottom of the table, the total. And the mean value of the variance of the three groups is known as the within group variance. And the difference between the total group variance and the within group variance is known as the between groups. Basically, what that's going to lead to is the test statistic, which is called F. So the F ratio is computed. So the F is the test statistic. F is the ratio between the sample variances, the between groups, and the within groups. So let's just look at what the table would look like and where the numbers are actually coming from, so we have a sense of that. The ANOVA table is composed of rows. Each row represents a source of variation, and then we're going to do the calculations for it. So I've talked a little bit about the kindergarten buddy program concept of giving students an extra hour of time after school, after a half day of kindergarten, to catch up for students that were behind. It was an interesting intervention program. And so you can see here, let's take a look at what we've got here. We've got three groups in this group. We've got the kindergarten buddy group, the half-day kindergarten group, and the full-day kindergarten group. And the means for how they performed on the phonemic awareness, I believe, was the test we had talked about last time. There are their means and the standard deviations associated with them. And then how many students were in each group. So the first group had 38, the second group had 37, and then the full day had 17. There were 92 total subjects in the study. So this is what the ANOVA table is going to look like. We've got the source of sum of squares, the degrees of freedom, the mean squares, and the F ratio. Nothing will be found in these boxes. The explained, and then the error and the total. So the explained has a different name depending on the type of ANOVA problem. So here's the sum of squares. And so calculated between groups, and then the error, which is the within, the between and the within. So to get the degrees of freedom, the groups. So there are the three groups, and we do degrees of freedom, one less than the number of groups, two. And then for our other variable, we had 92 total students, less the three groups. That gives us 89. We add the columns to get the total columns. That's pretty straightforward. And then to do the mean square, we divide sums of squares by degrees of freedom, and we get the mean squares. So that divided by that is that. And then the F ratio is 261, the mean square of the group, divided by the error. We get the F statistics, 0.759. We'd round that if we were reporting that as 7.76. Then we look for the p-value. So you would actually find the p-value in the final column, and that'll tell you whether this is statistically similar or statistically different. These are the rules for calculating the ANOVA on the SPSS. You do the calculations all at once, and then you interpret it based on the information. So you pick the information you need for each one, and we'll have a separate video to show you how to do the calculations. The things you're going to be looking for are the descriptives, the estimates of effect size, the homogeneity test, and we hit continue. So this is the basic what you're going to click situation. I'll show you exactly how to do that. And then we're going to interpret the descriptives, the Levine's test, which is our homogeneity test, and the ANOVA table, which is our omnibus test to let us know if there is a difference or if there is not a difference. Lastly, we've selected effect size. So when we click on effect size, we're going to get the partial eta squared. That's the effect size statistic for an ANOVA. And there's different values. And here we have smaller values for partial eta squared, and that's how it's calculated. So let's go to our next video to see how we do this in SPSS.